specifically to send them an email.
I didn't do that. I just added them earlier this week.
Yeah, I added them and thought everybody had an email, and then I mentioned to one of them, and they're like, "No, I haven't seen anything." What? And I went to go look, and I was like,
Send email. Yeah. That should just be automatic, right?
everything I've ever done where you put in a recommendation, like you put them in, and it sends an email, and that's it.
Did Dr. Granty post the new?
How much more edits do you need on your papers?
I mean, we're pretty much there, but I think there's some sections of my science case that need to be rewritten because basically a new survey that comes out that has come out, or a new catalog's come out that kind of changes some of the things that are in there.
Normally I could track in some way.
I'm gonna probably need to
Yeah.
get an extension on this most recent homework from Medici.
I'm still trying to get the last one.
Honestly, I really
Yeah, so
Eigenvalue
I'll probably
functions
ask
is,
them
like, one of the
whenever
things that I
they're-
did most consistently at work.
Like,
Yeah.
And so like I use
It's,
those decompositions in machine learning applications in the medical field.
it's
I
just
know
a
them.
lot, and then,
I've never seen the assumptions that
not
are going
complaining,
in,
but I got added on
like
this other
and I'm
TA,
I
so
don't
that's
get it.
like a bunch of grading that I wasn't expecting
That's like funny.
that I'm trying to
like
do
actual application using it,
on
but,
everything
like,
else.
You see it used
And
in another like sense. Your intuition's telling you.
Yeah, for real.
Kyle, or an odd negative, or an odd number of them.
Or an odd number of them. I don't know why I looked at that and I thought, I want to cause chaos.
I love how all of our little jokes keep on, coming full
Coming
circle.
back, because they're just good jokes. I do like that though, or an odd number.
I'm out of the loop.
Me and Kyle were talking about our homework, and like we were like, oh, we're missing up a minus sign, and like to me, I thought I was like, oh, that's something that Paul DeRock said, and like he was like watching someone's lecture, and someone was presenting, and in the middle of it, they're like, oh, it seems I made a sign error. And then Paul DeRock just like casually says, or an odd number of them. Because like negative.
Classic.
But then they posted their, where they did a study session for math physics, and they had all the equations and everything they worked on the board, and I just popped in to be like, you dropped a negative.
Or an art.
So
I'm getting better.
Okay.
He should be coming.
It's Sarongo, yeah, I ran into him a little bit ago, he should be
Yeah,
here.
okay, yeah, let's start it. So far we finished chapter 3, and chapter 3 basically introduced how to establish quantum mechanics theory. We have basis on 5 postulates, right? And we try to interpret all these physical implications of the 5 postulates. So now we are going to apply. We have the theory, we are equipped. And now we are going to try to how to apply the theory to solve the detailed system. So now let's first remind us postulate 5. That means for any system, state of any system, follow the Schrödinger equation, and that is a state change or evolution follow this, right? So now for this case, depend on the behavior of Hamiltonian. If Hamiltonian depend on time explicitly, then we have solved this, and that is a topic in chapter 10, next spring semester. Then, if in most cases Hamiltonian does not depend on time explicitly, so we know we can decouple this Schrödinger equation into 2 parts. The first one only depends on time, so we have the solution, which is less like a phase factor, right? Time dependent. Second one is this one, the Hamiltonian applied to this. To the cat, or state equal to this. This is eigenvalue problem in terms of chapter 2. Now, we also say that is time independent Schrödinger equation. So by solving this, then we will have the eigenvalue correspond to Hamiltonian, that's the energy spectrum. Associated with each energy spectrum, we have eigenstates. So suppose we have this. Then, for this case, we call that the state is stationary, since we know this probability at any time equal to the probability at 0, and that any states at any time can be expanded or make a superposition or linear combination of the eigenstates of Hamiltonian. So from here, now here this is a phase factor. Here we have an eigenvalue En. This coefficient Cn is the initial states project to the corresponding eigenstate. So that is what we discussed, right? And for this one, so now for this case, we are going to key solve this, right? So to solve this, we will have Hamiltonian. We know that's kinetic energy plus potential energy operator. Kinetic energy. Okay, let's just if I use this one. This is the position presentation, right? Let's just use this case. So we know this is a general. That each system difference is the potential, right? So for giving the potential a different type of potential, the Hamiltonian different, when we solve this one, give different spectrum, energy, and states. So that key is here. And now our job is the chapter, from chapter 4 to chapter 9, we all deal with time independent Schrödinger equation. That means we do not consider this case. We just consider this case. So we have a lot of story about this for different systems. That is given in this case, right? So now we will deal with this, and also this one has a symmetry. Different systems have a different potential. The potential may have a symmetry, and as we learn the symmetry associated with this symmetry, we have a conservation. Then also the energy is maybe continuous spectrum or discrete spectrum, and the states eigenstates may be bounded or unbounded. Or bounded. So those are the possible. It really depend on the potential and on what is initial energy. So now we are going to deal with the first case, one dimension, chapter 4. Let's start from one dimension first, then we go to the 3 dimension, right? One dimension, and then we are going to jump to the 3 dimension. 2 dimension, 3 dimension similar. So 1 dimension, we know that only linear motion, right? No rotation. Therefore, that is we start from here. Then if we want to from 1 dimension go to 3 dimension, we need also add another type of motion, is rotation. So chapter 4, 1 dimension, and chapter 5, before to deal with the chapter 6, the 3 dimension, we have discussed angular momentum. Introduce angular momentum property, then we are going to discuss or get into the 3D. So now let's start from 1D. 1 dimension, that is, of course, we always use the reference. Most cases, it's a position representation. Okay. Now, before go to the detail of each individual system, let's discuss in general. The property, general properties of 1D, right? 1D motion. Okay. So now let's first, as I said, that this different system, the key is this one, right? The potential. So now let's in general, the potential like this, is it as a function of x since one dimension, right? Something like this. We have stack, left-hand side, right-hand side, we have some of value. So assume that this one is go to infinity, we have value V1 and V2, and here we have a V minimum. So that is the type of potential. It's possible, so we will discuss like this. Then with this potential, let's consider, as I mentioned, whether the energy is a continuous spectrum or discrete, or the state is unbounded or bounded, depend on initial energy. So suppose if the initial energy is here, E1, and I have E2 and E3. So now let's discuss the three cases. Okay, so now let's first discuss if E equal to E1, which is larger than V1. Okay. So what happened here? Classically, you know that we will very free the particle between the positive infinite and negative infinite will go freely, right? And in quantum mechanics, kind of that when it comes to here, there are some of details, but it is, let me do this. So for energy, that will give us a continuous spectrum, and this state is unbounded. No boundary condition, right? So in this case, there's no boundary condition. Or the condition is infinite, right? Since no boundary condition. That is the first case, when the energy is higher than V1. So higher than the first highest. Then the second one is energy is, in this one, that is smaller than V1 but larger than V2. What will happen? So in this case, we know classically the particle is free from this side. So now let me give a x1, x2, x3, right? So in this case, we have a turning point, classical, right? Turning point, and we are going to discuss in quantum mechanics. So classically, turning point means the particle will move free in this from the less than x1, but x1 will turn back, will not penetrate or go to the position x larger than x1. There's no possible, right? But quantum mechanics here, it is okay. Okay, so so it may penetrate in the x larger than x1 region. Certainly, it depends on how the decay, right? How the potential in this depend on the energy here, then it will decay somewhere. So that is the quantum mechanics. This one is classical mechanics idea. But quantum mechanics, quantum mechanics we are going to discuss, it will be not zero. The probability to find particle inside is still non-zero. That is. So then how about this energy spectrum and the states here? Energy spectrum still continue. Continuous. And the states here, it is still unbounded. but we have the boundary condition. We have one boundary condition. X1, right? So what kind of boundary condition here? That is, that means psi. Okay. The function, if I use the function solution, is there are two parts. The first part is x larger than x1, and the second part is from negative infinite. So we have this. There are two different types of function, and then here the boundary condition is two wave function at these positions be equal. Right? That is boundary condition in this case. That is a turning point if you have this. So we are going to, when we deal with this, we are going to think about what kind of, at least before you solve the problem, you have some of the idea what kind of states and energy spectrum looks like. The third one is V minimum energy equal to A3, which is less than V2 but larger than V minimum. So you can see we have a two turning point, right? X3 and X2. So two turning points at X1 and X2. If classically we call that, then this is in quantum mechanics, it will penetrate here, that is classical mechanics. That means still can have this non-zero probability to find particle outside of X2 and X3. That is possible. So now we will discuss this, right? So that is the one thing that here this is only one, but now we have two. But then the energy. So the energy in this case is discrete. You will see that we will have to resolve is discrete. Most cases, the system will limited within this range between X2 and X3, and the state is bounded.
Is that right? You say two turning points at X1 and X2?
Sorry, X2 and X2 and
X3.
3. Yes, sorry,
Okay.
we changed it. Okay, so the boundary condition here, of course. So now the wave function here, we have three types in region 1, which is x smaller than the positive, larger than x2, and the second one is between x3 and x2. The third one is larger than negative infinite, but smaller than x3. Right? So we have three regions. That three behavior of this wave function. Then the boundary condition requires, because the wave function will always continue, as we say that physically accepted wave function speed continue up to the at least the first order derivative, right? So boundary conditions. We have these two boundary conditions, right? 3x3 equals to 2. And in this case also, we have a phi on x will go to 0 when x goes to infinite, since the energy is lower than potential energy, right? So you cannot expect that it will go over. It's just decay and then go to 0, right? So that's the case. And also phi 3. So when you solve the equation, we may have two solutions mathematically. then we are going to pick up the physically acceptable function. So that is what we discussed. Okay, with this one, then we have a two theorem, and then we go to the meteor system. So for this correct and the bounded states, there are two theorems that we will apply. So theorem 1, 4.1. Actually, this is okay. Let's say that in one dimension, right? So in one dimension, the energy level, okay. Let's just use this one. All bounded states. Is this correct? As I said here, right? That is also theorem give us this one. And non-degenerate, this one I will not. I think some case degenerate, so now let's just say that is this correct. That is true. And then this bounded states. So for the bounded states, okay, bound state has all systems. Here I have n nodes, okay, n nodes. And we know nodes, right? Node is how many nodes here? 0, right? No nodes. You have a node here, right? Node means that correspond to the function at that position is 0. So there's just no nodes. There's n nodes for they have eigenstate. Okay, let me part. I use the same part for x. But in this case, the ground state, that's the lowest the energy ground states correspond to n equal to 0 or n minus 1 states. That is no nodes. So n equal to 0 or equal to 1 depend on the spectrum. If spectrum start from n equal to 0, then ground state is 0. Then that state must be like this, no nodes. If the states, the spectrum n start from 1, then that n equal to 1 is this states, ground states. That is also no nodes. The first node states correspond to the first ecstatic states. So that is gives this theorem about this. Okay, that is okay. Yes.
So it's 0 for n is equal to 0 and 1.
For ground states, yeah.
But n for everything but that.
Or so that means in this case, if this one, we have a lot of this we call quantum number data, right? So n. So allowed n value, if allowed n value we obtain is from 0, then that one 0 is no nodes, right? So that stays in ground state. But if we solve the solution that we have the quantum number n is not from 0 from 1, then that n minus 1, that's no nodes, right? That is this ground states. Oh, okay, the nodes. Sorry. Then in this case, this means we have nodes, right? So n minus 1 nodes. So if n equal to 1, it should be 0 nodes. N equal to 2 should be 1 nodes. That is how to count. But this is, I mean, when we go to details, that is clear. So we just give a brief summary here. Now we go to the first case. The first case, a simple case, no potential energy, right? If you have potential, then solve this more complicated, depending on the type of potential. Let's consider start with no potential. What kind of system?
Free.
Free, yes. So now let's start from free part first. even free particle solution easier, but when we discuss physics, we need to be careful. So now let's first discuss one free particle. Okay, so if a free, potential 0, right? If you look at this general case of potential 0, then energy should be always equal to 0 or higher. Above 0, cannot be lower, right? So that is. Then if you look that belongs to this case, right? If a potential 0, so that is 0, then the energy always larger than 0, so you will expect the spectrum to be continue, state speed unbounded. So let's see. Okay. So if because 0, right, so the Hamiltonian is equal to t plus v, not equal to t, which is in one dimension is this term, right? So now let's solve this time incremental equation or eigenvalue problem. Is we are going to solve this, right? So now let's see. Okay, so that is solve this. Now since we are using the position representations, I remove this cap. These are all functions. Right, so that we're going to solve this. So left hand side is minus h down square over m d square dx square by x equal to energy by x over, I divided this constant both sides, so I have this solution, this formula plus, I multiply, so this became a negative and move to the right hand side became positive, right? So I'm going to use k square equal to 0. Here, k square I define as energy and 2m. Just that, okay, 2m e over h bar square. Right, I define this. So this solution is very simple. You know, there's a simple harmonic, right? Or exponential with oscillation, since it's plus. So the solution is very easy. There are two solutions. So now I'm going to distinguish. Okay. Plus, as use k plus. It is a function k, right? For given k, we will have a solution and plus. That is a kind of, if we ignore this coefficient here, but the function is, and we know this pyramid propagate along the positive x-axis, right? That is this one. Second solution for giving k minus right? Because these two are very simple, are solutions of this. If you substitute this into this equation, you find that is a solution. Okay, and then the energy. Since here you see there's no any restrict on k, k is continuous value. Therefore, we have also a lot of energy as a function of k. For given k, we will have energy. It is also continuous, right? So yes. And this spectrum are here and bounded. Since here, you see this is a pyramid. No any bounding. They can propagate or exist in the space from minus infinite to the positive infinite. So all are consistent now. We are going to discuss some of the physics in details about this solution. There are several issues we need to consider based on what we learned from chapter 3, right? The first is okay, let's save this discussion. First one. First I want to discuss is the current. So why we discuss parity? Now let's see. Remember chapter 3 we introduced parity, right? So if a parity, if I use apply any state, if it will give us, right, that is parity. And I use the null vector, that means this is parity operator. So now, let's see in this case. Hamiltonian is equal to t, right? So the Hamiltonian, whatever we change it x or change x equal to negative, it will always equal, since it does not depend on x. So Hamiltonian has a symmetry, right? That means H1, if you remember that is P and H, P inverse, that equal to H. So these two operators are commute each other. Do you agree? Because x does not depend on x, right? So whatever you change x from positive to negative, you apply the parity to this operator, it still keep the same. So if they same, then that means they will have joint eigenstates, right? In general. So now let's see, are they joint eigenstates of these two? We have this is eigenstates of a Hamiltonian. But since the Hamiltonian does commute with the parity operator, so we are going to find this common, that is complete setting of this commutative operator. That means they have a joint eigenstates, right? So now let's see if it is. Okay. Let's see this one. Since this one is, right, so now let's check. First check what with the plus minus I just put together, right? X is E I, okay. Plus became, the X became minus X. Then the minus X became plus, right? So that is E plus minus plus. Okay. Okay, X. It will not equal to negative, or not equal, okay, equal to plus minus. All right, so its eigenstates of parity. If you remember that if it is eigenstates of parity, right? So that is eigenstates of parity with eigenvalue either plus or minus. But this one is not, right? So that means it is not joint eigenstates of these two operators. Then we are going to construct, so how to construct or find, okay. The reason is also very simple, that we just discussed. Why? Who can give them the reason why? You see here, we have two states. For given energy K, then we have a given energy, but we have two states, that means degenerate, right? It is double degenerate, right? The degenerate. And in chapter 3, we almost we discussed in the midterm exam, the last problem. If one of the operator its eigenstates has a degenerate, then that eigenstate cannot form this joint eigenstates, right? We have to find another side such that is eigenstates of a parity operator and eigenstates of Hamiltonian. So how to do that? Because Y is this one, right? So now we are going to construct joint eigenstate. How to do that? Let's see, if this is not, then we are going to, I'm going to use another function. Let's use psi plus minus for giving kx. That is very simple, just at the half of this one. K plus minus 3 minus. Let's see. So now here, now I'm going to use, okay, that is in general, right? So now let's try to double check whether the construct, this is a twice this sign, right? So that's different. Okay, let's do plus. And also for giving k, that is here half of k plus minus x plus minus k minus x, right? And you can see when this became minus x, then they go to here. So that is plus minus, right? Just switch. Then I take this sign outside because this is a plus, I want to make the same, right? So that plus minus half of so that is plus minus psi plus minus k x. Yes. So if I construct, I simply add these two together, either add together that give us symmetric, and subtract together is odd. One is even, another odd, right? So yes, they are. And then you come back to see, yes, this is eigenstates of the parity. Now let's look, double check. If this is also eigenstate of Hamiltonian, check, right? So now we need to check. So Hamiltonian is minus h bar square over 2m d square dx square psi plus minus k x. And you can see here, since the inside the same, right? This is eigenstates of Hamiltonian. This is also eigenstate of Hamiltonian. And with the same value. Okay, let me just write it, do the intermediate step. So when you do the second derivative, right? So you will have, we have a half of this one. We have I k square plus k plus x plus minus I k square plus k minus x, right? When you do the second order derivative, then you take the I square is minus, right? And minus I square also is minus 1. So you will have this give a minus k square. This also minus k square. Come out, minus might become plus. So then you will have energy. Just keep here. E. So yes, it is also eigenstates of Hamiltonian, right? You have that is Hamiltonian applied states equal to energy multiplied states itself. So that is. So now, what this one is we construct is the joint eigenstates of these two operators. That is the first discussion about the parity. Then with this, we can also number 2 in general. So general solution or function in this case. That is, we discussed the construct this joint eigenstate. But here, we will not, if you do not really care of that, you just consider I'm going to give the eigenstates of this Hamiltonian. So use the linear combination of eigenstates with given k. You can also, in general, with a coefficient a plus associated with this one, and a minus. This is again the eigenstates of Hamiltonian, but not the eigenstates of parity. So that in general, if you do not care about these joint eigenstates, you still can go to here with this one. Then so this associated with the complete wave function or we call the states or stationary states of this free particle. Stationary state of free particle at any time is xt, right? So that is you can use this. Let me first use this one and later, because energy spectrum is function give a k, it will give us energy time is ft, right? Function, and multiply spatial part is this function, so that is kx. Or if okay, or we multiply inside this term, so we have a plus exponential, we have I, so I kx minus ek or hrp, and the plus a minus multiply exponential minus I kx minus plus yeah, plus because minus meant plus, right? Plus e k hrp. Or we introduce omega, so not kx minus omega kt plus a minus exponential minus I kx plus omega as a function k t. Then we have the given notation here plus. That plus x is the plane wave propagates around this positive x-axis, and another wave is just opposite direction. So here omega k is ek over h bar, right? We just introduced. So that is h bar k square. Okay. K square. Okay. That is the second topic. Now, number 3. Let's see the probability density. Density, if we define that one. So that's B plus minus T square, and that is, I introduce plus minus. Plus is the first term with the A plus, the coefficient, minus this minus. So, okay, that's first. Okay. So here, that is A plus minus, which is a constant. What does it mean? The particle, free particle, move in the space at any time. The probability is always constant. There's no any information about which time the particle where. So that is some question here we are going to raise the question and we are going to discuss. Okay. The interpretation, I think the interpretation that is give us a free particle travels to either to the right or left. Okay, please will define what? Momentum P. This one since it's one dimension, I do not use px as p, right? P is p plus minus is plus minus h bar k, right? And energy is the generator. So what does mean? When we have a k, then we have a well-defined exact momentum and exact energy for this state. So that gives us this. And then there's a question, right? Second question here. The question is now we have a question. So let's answer the questions. The first one, because the delta P equal to 0 and delta E equal to 0, according to this Heisenberg uncertainty principle, delta X equal to, remember that, let me just try to remind you. O is value equal to half of absolute value of X P, right? Remember this? And that is h bar. Because that the commutator is h bar, then the absolute value is h bar. So that means then delta x is, okay, always larger or equal to this one, right? But now delta p is 0, so that means let's go to infinite. What that means, okay, if this state really characterizes a free particle, we can exactly know what the momentum, linear momentum is. However, how can I find it? The uncertainty is infinite. And that is impossible because free particles be localized, somewhere located somewhere, right? So this is not correct. The question is, if the solution is correct from this mathematically, we got this, but this is a question. Yes.
Is this in some way tied to relativity, that you have to measure location or position of an object in terms of something else? So the only thing that we can measure compared to is a potential of some kind, and because we can't do that, we can't have a measurement?
You mean when the measurement is state change, right? Okay. Because this state is eigenstate of Hamiltonian. So when we measure, and also actually, if you want to, for given or well defined means this state is well defined. So that means when you measure it, still will not change. If it is linear combination, you measure this one, right? So but this the state of this itself, like eigenstate of the momentum. So when you measure it, still keep the same state. The probability is 1, right? That's answer your question? Yeah. Or, I mean, you can, if you, let's say this one is minus h bar dx, right? So you apply this one, you have a k, right? You have an exponential here, you have a k to ik, right? So then you have iki here, then you will have, okay, just whenever you use this one, or just simply use one, because this linear combination is the same. So, then that is minus I h bar. Then you have this, I mean, either plus minus, right? So you will have a plus minus of ik, right? Get out from derivative. This one, another one. And minus I h bar. Right? And then this one is I, so this is a plus, right? This became a plus minus k h bar. This stuff. So that is a P. So if we measure these states, if it will give us 100% of this value, which is momentum, and state will not change because it's eigenstates. Right? Remember we have this eigenstates will go to prime, but this prime be one of the eigenstates of right? Remember this? But if this one already this, it will give you will not change. So that is this case. If this is really the state of the free particle, then if we measure, we can give a well-defined momentum. Then according to the uncertainty principle, we cannot determine where it is. The fluctuation or uncertainty of this position is infinite. So that is question. That means that is not good wave factor to wave function to characterize free particle. Similarly, like this, if you consider energy and energy pair is delta t, right? Delta t go to infinity. So that is the question, first question. And the second question, let me see, questions 1. Second question, let's see the normalization, right? So now the total probability, if we say the total probability is from minus to infinite, right? And the plus minus, right? That is definition. And you will see this one. And you can see that is a square. If it takes the complex conjugate is minus. So that term, I think you can set this is a plus minus square dx. A plus minus constant, so that is a plus minus constant multiply infinite, right? If you integral the x. So that is impossible because probabilities be always 1 or then you give the probabilities infinite. That means this is not good wave function to characterize free particle. Second question. Third question. Okay. So we have for the velocity because this is a plane wave, right? So according to plane wave, the speed of the wave. That is, we are going to use v wave. That is the relation between this frequency and the k, right? Which is, we already have this here, right? This frequency is h bar k squared over 2m over k, so that is h bar k over 2m. So is this characterize the speed of the free particle? Let's consider classical. So classically, we know that for a single particle, a free particle, the speed is momentum over m, right? If we have a linear momentum, and the linear momentum is here, we already have. That is h bar k over m. So that is if classical, your quantum mechanics cannot give a totally different result compared with classical if it describe the free particle. So this is twice of the speed of wave propagate in the space. So what that means, if the speed which we use this wave function, which is a plane wave, that propagate speed actually is only half of the real particle speed. So it is okay. So it is equal to that means v wave is not equal to v. I just use v as a particle, free particle is the speed, right? So that is a third question here. Why? Okay. So to answer these questions, is easier or is mathematically can give is okay. The wave function of a free particle actually is not plane wave. Free particle. We have you see here, the key is here. We have several keys here. Because the question here, that means the exact P. So if the delta P is not 0, that means there is a probability of fluctuation of the momentum. And this one is only well defined. So we need to add sum of different momentum together. That is superposition principle, or linear combination of different P. Then this make this one become a non-zero, right? So that idea is linear combination. So that is a big packet. Now we have, so now we are going to introduce, now let me first give the formula and this is the normalized factor here. So now we introduce phi as a function k, and you know the k, here only one k, but now we are going to consider linear combination of different k in the k space. So all the factors, and you see here, this is plane wave, right? Now you can see what happened. This is just like kind of a superposition principle. Principle, or the linear combination of all k. So we immediately solve this one. Now delta t is not 0. It's a sum of a finite fluctuation, then give us also the fluctuation of x become a localized from this spirit whole space delocalized and become a localized behavior. That makes sense. That characterizes this the particle. Then automatically we will prove that this one will not go to infinite, it will go to finite. Then here we will also solve this one, because if we have a wave packet, the wave packet is a combination of all the plane waves together and move as a wave packet. That speed is not this one, and not characterized the free particle, right? So you see the answer is only this one, and then we can answer all the questions. Now let me first give this k phi as a function, that is k. It is the amplitude of the wave packet. Okay, now I call this as a wave packet, right? So this one is, we call the wave packet. This part, chapter 1, there are some of, if you want to go to details, chapter 1 and chapter 3, chapter 4, together, all the information discussed here. Okay, and then it's given by the Fourier transfer of this initial states. Transfer of initial states. If we have the initial states, what it looks like as here. K is and this initial states, right? This is a Fourier transfer. Okay, you may ask, how can we get this one? Let's use our technique learned in chapter 2. So hopefully that can help you to understand where it comes from here, right? So now, let's consider initial states. This one is the wave function of a cat project to the position representation, right? Okay, let's say this one, right? And then I can insert I unit operator between these two, right? And this unit I'm going to use the basis, which is the plane wave we obtained, right? So that is, because that is continuous. Remember, if for continuous, this one is integral, right? And I'm going to use k Okay. Okay. Right, then this one is unit operator, right? This one indicates this one. So now you see this is the project, this function project to the x position. That is the this function, and this one is actually this one. Okay. So we have here. I'm going to write that is nothing but this is k. Okay, that is k x and okay. So here, this is nothing but this the eigenstates of the Hamiltonian for free part with a given k project to the position representation. That is exponential. This, if we have this rating factor, so we want to have this normalized, so we can use this one, right? Remember this. And initially we have this solution. So that is this one. Then this one is the phi. The initial states project to the eigenstates of Hamiltonian with a given k. Okay, and this one is that defined, that one. It's a Fourier transfer of this. Okay, so now I think I will write down earlier. So that is Fourier transfer. So the given k, then that is this integral, right? So that is this one. Because this is the states that they belong. So we have a negative, and the cat is itself. So integral is the whole the space. That means project to this state in the position representation. So we have this. Okay. Then that did I already write down? Okay, so then this that's enough. So then this is for the zero states, and t naught. So t is the time multiplied time, right? Exponential minus I e h bar t and sine h bar. So that is that. This one is here, right? So that is the proof. Okay, x is this term and this one plus this exponential, so that is exponential. Phi k kx, and this is a minus, right? Minus omega t, since e over h bar is omega t, and d k. Okay, so now with this one we are going to normalize. Let me see this class. Normalize, right? So we have proof. Get this. How we get this one? Then we are going to see whether it is square in finite. We are going to check if it is a finite square integral. Right? If it is, then physically acceptable, right? So that means we are going to look this term. Integral for whole and dx, right? We're going to look this one is finite or not. We're going to double check. Is it finite? Okay. That solves the second question. Remember that is if a Plymouth it will give us infinite probability. So, or normally, so this gives us, okay, now let's do that. For each one, right? So this one is this, or from here. From here, and take the conjugate, so here we have a magnetic. So you will have, let me just give you the details. You will have 1 over 2 pi, since we have a square root, 1 over 2 pi, and multiply twice, so that is square root disappear, right? So then we have that integral. It corresponds to this one, and another not for k, right? So we have 2 integrals for k and 1 integral for x, so 3 integrals. dk prime, since we do all together, so we are going to separate or distinguish. Then for this amplitude of k prime by k, and then the exponential, exponential term, as exponential, we have I for omega. Omega term is k minus omega k prime t. And then that is for k, and then we have x from minus to infinity x. So then we have this exponential for this one, ikx, right? So we have I k minus k prime x dx. That is a total 3 integrals. Now the 3 integrals, if you remember this one, we already discussed, that's a delta function, right? With a factor here. So now, so that is a delta k prime. Then you see we have a delta k prime, then there's with an integral k and a k prime, only the k equal to k prime, right? So we have only k from minus infinity to infinity. So 2 integrals disappear.
Dr. Yu,
Yes.
I'm a little confused at where you got the k and k prime integrals from.
From here. First one, this one, is k, right?
Okay.
And I have upside down.
Okay.
Another integral. So I distinguish the 2 integrals, I have used k prime.
Mm.
That makes sense?
Yes.
Because here we have this one.
Okay.
So then we have a 2k. Then
Right.
that y for
So
that.
inside of the integral of x is k and k prime.
Yeah. And this one's x.
Mm-hmm.
So each individual has associated with a k.
Right.
So we have 3 integrals.
Okay.
Yes.
I am curious why when we, like mathematically, I get it physically, but mathematically, why when we prove that k prime is equal to k, the second integral doesn't drops away and it doesn't become just integrating it twice with k?
Not proof, because this term, if you remember this one, divided by this is a delta function. You remember this?
Yep.
So that means, now, okay, if not, I just write again. Okay, I write again, so now keep continue dk, and dk prime I still keep, right? dk prime. Then here, I keep here, k prime, okay, and exponential I omega k minus omega k prime, t, okay, and multiply delta k prime, right? So that means this integral with k prime, only with k equal to k prime, that's non-zero. Otherwise 0, right? So that means this is reduced to only one integral, only for dk. The others 0, so then all k equal to k prime equal to k, so now this is nothing but square, right? And then omega k minus omega k prime, because k equal to k prime, so this is 0. So, we have it. So you see what happened? This must be finite. Or we can also normalize. Because if you remember, we have here this finite if the integral of the initial function is finite. And the initial states for this one, with packet, and we know that integral is with packet. What do you mean with packet? Is something like this, right? That's an x. That is the packet. So if you do this integral, whatever t equal to 0, that's be finite, right? So our initial states, and what is initial states of still with packet of initial, then this integral must be finite. If this finite, you come down here. This is just Fourier transform. It's also finite, right? So here is finite. If this finite means this is finite. That makes sense? So if they finite, okay, so the second question about this probability. Now, physically acceptable because it's a finite square integral. But that's the second question. The third one is about speed. About speed of this the free particle, which one is correct? At least the first, the speed of the plane wave, it is not correct, right? So now let's look if we introduce the wave packet. How about this one? Now we're going to the second question. The third one is how about the motion? And answer this question. Motion of wave packet. How about this one? Let's see. So we are looking for this omega as a function k, right? Let's make the Taylor expansion around the k naught. E omega k naught plus pi order, right? And as we already discussed here, this is a finite. This gives us the distribution is like pig, not like plane wave is flight. So we will know that that's be in the k space. There's be expectation value if we say the k naught, and that fluctuation is the k along the k naught, right? So we can approximately up to the first order. Let's see, okay. Then we are going to introduce S is a difference. Then K is S plus K naught, right? If you define. Then here, okay, after definition this one, if you know that the dimension here, so that should be V, I'm going to say group, is the speed of this, because this is velocity, right? If you see the k multiply velocity is give the same dimension of omega. So this in dimensions be a kind of velocity, not like definition. We do not know what is, so now let's give this. So that means I can write down is in terms of k naught S G, right? Okay. Then let's go back to see the wave function. Wave function, just rewrite that this is a wave packet, right? From minus to infinite, now this is amplitude of this and exponential term kx minus omega k p dk, right? That is the packet, the formula. Now we are going to substitute the omega k, this formula here. So here, exponential I kx, I still keep here, minus omega k naught minus s v group, right? T. Oh, sorry, T. Inside omega k naught minus s now I'm going to replace k by k, this one, s plus k naught. So if I do this, you can see ds is dk, right? So that is because k naught is constant. So here, I replace k by k naught, so now, and s, so that is by s plus k naught, exponential I, s plus k naught, x, and here, I'm going to minus x plus k naught v gt. Okay. First to here. So what I did is I have a minus. This one is this term, right? So I add another term. Is minus s as a minus k naught vg, right? So add this one, I need to have a plus. So plus I k naught vgt, right? This term minus, so then that, and then here I have another term. This is a minus I omega k naught t. Okay. I just add term and my subtract term, so because I want to have this term constant. So now, since these are constant, I take outside exponential minus I k naught. Okay. Since okay, I didn't. So but this one is nothing but k naught. This one is v for k naught, because we know that omega is h bar over k. Right, so that is so we have this. Let me write that in so first. First, do we k naught minus of here. Let's do it this one. So here we have I k naught v with t and minus I omega k naught t. And inside integral is ds plus k naught I s plus k naught, and multiply here, right? Multiply exponential I s plus k naught multiply x minus v g root t. I see, yeah, okay. Just simple, I use g here, that is a group. Okay, so now you can see here and yeah, that's enough. So you see this function here. All our function s plus k naught, x plus k naught. So that is, I'm right down here. That is, if we select x minus v group t is another new position. So that is x prime, t equal to 0, right? This term. Because no any others, right? This is x. And then this term, I'm going to this one is v with omega t k naught. Okay, so then this one is I'm going to take I k naught minus, I take this outside, so that is a v with minus v group t. Multiply this one. That is important. So what that means, you can see the probability, if I say that is the wave function at any time is this one, so probability is, because this one equal to 1, right? So that's the exact same as. So that means the function, this function actually calculates the same shape of the at 0, at t equal to 0, but the only difference is the peak position start from x to x prime. So x prime is x move with this velocity. And that gives us, okay, so that's right. Oh, I think that we just plot the curve and let you understand what this just means. So here, initially, if this is a t equal to 0, right? So then at t equal to non-zero, we move to another position here. With the speed, so this is a V group T, right? That is, so this is x prime. So that is the speed is the wave packet with the speed move. So you see here, what happened is it still keep the same shape, and then the shape keep continuing to move, and this speed is this one instead of a wave. And this speed we already, I think, did I? Okay. And now we come down to here to see this group. Wave group is d omega k dk when k equal to k naught, right? And if you remember, omega is h bar k squared. Then dk, so we have, okay, it's a d h bar k squared over 2m, right? Remember, this is omega dk. And 2 to 2 cancelled, so that is h bar k over m. That is nothing but the speed of this free particle in the classical physics. So yes, wave packet can really characterize the behavior of the wave state or quantum states of the wave particle, since they can satisfy all the physical interpretation that everything. So then this one also gives us a fluctuation of momentum, since it's a linear combination of all this k, sum of the constructive, sum of the destructive, and then they form this packet with this speed. So now you can image. In quantum mechanics, to characterize free particle, you can there's a wave packet moving in space, and of course, the values of this depend on initial states, right? How sharp peak or how broad peak depend on how this linear combination of your k, then depend on your initial. This is initial states, right? Initial. Then they control this. So what happened is this. Then the probability now, this one, is finite. Since now delta p is non-zero, right? It is also finite. So everything solved. Okay, any question? This is we discussed the free particle, and this one mathematically is not complicated. You can easily solve the equation, but we need physics to see, to check our solution mathematically whether it is acceptable physically or not, right? So that is discussed. After that, in any case, when we deal with the system, we have the solution we need to check. All right, okay. So next Monday we are going to discuss another type of potential. Then you will see the solution either has this bounded, unbounded, or continuous spectrum, or discrete spectrum, or degenerate or non-degenerate, depending on symmetry of potential. Here, the reason why it is degenerate because symmetry potential has a symmetry, right? Then if we have another potential well, which is also symmetric, then also degenerate, right? If not symmetric, it's not degenerate. So that is the other examples we are going to study and see. different type of the behavior. Okay.
They're always so slow down there.
Yeah.
Yeah, something like that, yeah. Yeah. They're not good at anything down there. Dining services on campus are really kind of a joke at this point anyway, so.
What do you mean we got sticker bars at the bookstore? Or Reese.
Yeah, that's the best place to go for a meal is the bookstore.
Good. So good to see you.
Classic moment during getting so lost. Alright, let's look at the syllabus. What do I need to ask again?
That last part, I just completely blinked out. I need to like dissect this video later.
It was borderline the same thing. I was like bleary-eyed. My brain hurts. My hand hurts from writing. I've lost all track of any physics of what's going on. I don't know what's happening. She's like, so yeah, not very complicated.
Yeah, no, he was checking the time. He was
So,
Yeah.
I was like, I'm glad I don't feel like the only one. Is it raining? I don't know. I can't prepare for rain. Because I wasn't last time.